Thanks again for the introduction. And as described earlier, I'll be presenting my recently accepted paper called FairTune, which is basically a framework that we proposed that allows you to fine-tune your model in a way such that you ensure fairness or you improve fairness for your downstream medical task. The paper and links to the code are given in the slide as well. It's all open sourced. So first I'll start with the background, the background problem and why we even began this work. So we have seen a lot of work on vision transformers, and this is an example of the architecture of the vision transformer. So this is a block in a vision transformer, and we have different variants: VIT base, VIT large, VIT huge, and basically what those VITs differ is the number of these blocks. But essentially, a vision transformer is made of these identical blocks, and each block contains certain subcomponents. So, for example, if you see norm one, which is a normalization layer, then you see an attention subblock. Then you see norm two, which is another normalization layer, and then there is another subblock for an MLP, and this constitutes a block. And then these blocks are repeated several times, and you get your vision transformer architecture apart with a few other things as well. Um, the base variant or VIT base contains 12 such blocks. And this is just the primer that I wanted to give, and it will make sense later in the presentation. And now I'll talk a little bit about what parameter efficient fine tuning is. So, parameter efficient fine tuning, you must have heard a lot about it more recently. And in very general terms, it is a way in which, given a pre-trained model that is pre-trained, it can be a vision transformer, it can be a large language model, it can be anything. But given a model, we do not, the traditional way of fine-tuning a model is basically updating all the parameters of the model. But in parameter efficient fine tuning, we take a slightly different approach. We freeze the entire model or most of the model, and we fine tune very selected parameters in the model. So I'll give you an example of that. Attention tuning is a form of parameter efficient fine tuning method. And it says that if you're given a VIT, you can freeze the VIT and you can fine tune just the attention layers. Similarly, we have another method called layer norm tuning, where you freeze the entire model and you fine tune just the normalization layers. And then there's another one which is quite famous in natural language processing community, and it's called bitfit, and where we freeze the VIT and we fine tune only the bias parameters. So if you see, these are some, these can be considered as some special properties of transformers as well, um, in the way that here I've highlighted the attention subblock, but the transformers contain these special properties that you can fine tune either just the attention block or just the normalization layers or just the bias parameters, and you'll get a very good performance. So that is one thing that we observed or we came to know. And my previous paper showed that parameter efficient fine tuning is very effective, especially in case of medical image analysis, because in medical imaging, the data sets are not too big. They're very small to medium sized data sets. And when we are fine tuning foundation models, there's a chance that the model might overfit on the small data sets if you are updating all the parameters of the model. So if you employ parameter efficient fine tuning, you can get very good results in medical imaging. And that's another paper. And our takeaway was that certain layers such as attention and normalization layers, they hold significant importance. And fine tuning just those layers is a very effective fine tuning strategy. And now the premise of the work. So the setting is as follows. You have a pre-trained model, which is a VIT in our case, and you have a downstream data set. And since we are working in medical imaging, so you have a downstream medical data set. And this data set has two different types of information. It can have information on a sensitive attribute, for example, the skin type or the age or the gender, and also the diagnostic label. So to give you an example, consider you have a data set that has a data set of X-rays, for example, and the diagnosis is that an X-ray can either be COVID-19 positive or COVID-19 negative. But additionally to that, we also have information about each patient or each image in the data set. Like what is the age of each patient in the data set? What is the gender of each patient in the data set? So that is the setting that we have. And there are several ways to define fairness, but how we have defined is we say that we measure fairness through performance of the worst performing subgroup in a given data set. What this means is that if I have a data set of X-rays, which has, and I have information on gender, male and female. So the performance of whichever subgroup, male or female, is giving me a worse performance, I will take that into consideration. And my ideal goal is that I want to minimize the gap between the two subgroups. Same thing for age, same thing for skin type. I want to minimize the gap between different subgroups, and that's how I can say that this model is more fair. We asked several questions. So our first question was, can employing parameter efficient fine tuning lead to an improved fairness than standard fine tuning procedures? And the second question was, can we further optimize the existing parameter efficient fine tuning methods for improving fairness during fine tuning? So I'll focus on the second question a bit more. For example, I have decided to use a method called attention tuning, and I'm tuning all the attention layers. And I have seen that if I fine tune just the attention layers, my model gives a good performance and it is also less biased, or it is more fair. But the second question asks, can I optimize, can I take this one step further, and can I for example select which attention layers should I need to fine tune uh, to improve it even more? I mean, it might be possible that we don't need to fine tune all the attention layers, but certain attention layers, and that can give you an even better performance. So this is something that we wanted to explore as well in this work. So now there were certain motivations for our study. Um, Previous studies have shown that majority of the existing methods that have been proposed in the literature to improve fairness, they're ineffective when applied to deep models. And there was another paper from our group which was accepted in ICLR last year in 2023. And it's a very big and extensive benchmark. And what they found out was that you cannot there are so many methods proposed for improving fairness, but none of the methods could surpass ERM with a statistical significance. So basically, if if you constrained all those methods under a common procedure, you find that full fine tuning is still the best result, and all the methods that have been proposed, especially to improve fairness, they're not working very well, and that's a major problem. So, and the methods that have been proposed, they are found to be more effective on shallow models when applied to tabular data. But currently, if we consider the case of working with a foundation model or a very large model such as VIT, those methods tend to fail. And next, there was a very interesting observation that we found initially in our work. It's that these high capacity models, such as VIT or any other big model you can imagine, these models are over parameterized. And deep models, and the problem is that these models can exhibit perfect fit during training data, and that results in near perfect fairness during training. So if you see the first graph, I'm plotting three things, and this is during training. So I'm plotting the overall AUC of the overall AUC of the data set. I'm The next orange line is AUC of the best performing subgroup. Let's consider that was the male subgroup. So the best performing subgroup is the orange line, and then the worst performing subgroup. And we see that during training, it's exhibiting perfect fairness. I mean, you can barely see the difference between best and worst performing subgroup. But when we observe the same thing for the validation set, we see that the overall AUC is fine, the best performing AUC is fine, but the performance that, or the subgroup that suffers, is actually the worst performing subgroup, and we see this huge drop in the performance. So we see that bias can also result due to our models not generalizing properly. So now what we need is a method that enables good generalization, that controls the capacity during generalization, and that prevents overfitting. And how can parameter efficient fine tuning even help in this case? Because in parameter efficient fine tuning, if you recall, we are not fine tuning the entire model, but instead we are fine tuning a very, very small subset of parameters in the entire model. So we have, in a way, we have controlled the capacity. And it has been shown previously that there is no compromise on performance when we are doing parameter efficient fine tuning. So both of our goals are met. And yeah, I mean, these are the 3 points. Basically, parameter efficient fine tuning can regulate the capacity, and also there is no compromise on performance. So that is what we selected, the experimental design. Now, this is where, if you pay attention properly, you will understand this entire framework. Everything before this was basically a primer, and this is where our method comes in. So we can, so basically, we can decide to fine tune certain layers of a model and freeze certain other layers of a model. And doing that is very simple. For example, if I have a given pre-trained model, which is a vision transformer, and I also have a binary mask containing only zeros and ones. So wherever there is a zero, I would say I want to freeze this layer. And wherever there is a one, I would say that I want to fine tune this layer. So if you see this random mask, this basically means that freeze the zeroth layer, fine tune the first layer, the second layer, then freeze the third layer, and so on. And if you also see the length of this mask, it is 12. And the reason it is 12 is because a vision transformer base variant contains 12 such blocks. So in a way, each element of the mask denotes a block, basically. Are there any questions until this point that I can take?
Yeah, I had one question. So in
Yeah.
the previous slide, you mentioning like if we selectively fine tune some specific layer, then the performance over the worse effective segment can be improved.
Yeah.
So I'm just not able to get the rationale. Like the experiments are fine, but like what maybe the rational explanation which you can give, like it will affect the performance over the particular group where it was having less accuracy, and it won't affect the accuracy over the other group.
So are you talking about this slide?
Yeah. Like here you showed like it happens. Then in the next slide you mentioned like if we do parameter effect like selective parameter fine tuning, then this gap which we are seeing here in the green and orange or blue in the
Yeah.
second plot, like that can be reduced. So
Yeah.
I'm
So
just
that
trying to
was
understand like the rationale, like why it should be.
right. So the
Yeah,
reason,
I
the
have also
reasons.
follow-up question. I mean, why
Yeah.
this is happening? I mean, in training there is, fair, it's fair, but I think during test time there is a gap between the best one and the worst one. I think the reason I'm also not able to get, and why it's happening.
So there can be several reasons for it, but the reason that we came out, and the reason that certain papers published previously have also shown, is that if you're working with a model that's very large, um, it is very over parameterized for our downstream task at hand, or it contains way too many parameters for the task at hand. So when you are updating way too many parameters, there's a chance that some form of overfitting might be happening, or generalization is not, or the model is not generalizing properly. And what we show here in this graph is that if the model is not generalizing properly, it mostly affects the performance of the worst performing subgroup. So if I have another
So
model
that's why you
that,
are saying that. Okay, that's
yeah,
why you are saying that if we just frozen few parameters and do a parameter efficient fine tuning, then all the parameter you won't be fine tuning. So maybe the chance of overfitting will reduce, right? So that's
yeah,
kind of the intuition. Okay,
yeah.
got it.
And
But
I
still,
mean,
like we are not reducing the parameters. So even if we fix some of them and fine tune some of them, and then you say like it bridges this gap, which we are seeing here.
yeah, I mean, that is our hypothesis. So the reason for this gap was basically the capacity of the model. And if you are fine tuning a very small subset of parameters in a model, you are reducing the effective capacity of the model. And we had this hypothesis that if we reduce the capacity, maybe we would be able to improve the generalization and bridge this gap.
Then don't you think like it the overall size of the model will also play an effect? Like the if we take suppose GPT-4 and
Right.
I fine tune, even if I selectively like fine tune a specific part of it, even then I can't mitigate the impact of the remaining, the already learned language, which oh sorry, not language, the already learned knowledge it has.
Right. And that is something that we don't want to do. I mean, the idea behind parameter efficient fine tuning is that if you already have a model that is quite powerful, and it is pre-trained on something, we want to reuse those features, but we don't want to update the entire model. I mean, if the model has already knowledge about a lot of things, we don't want we don't want to update all the parameters of the model at the expense of learning a new task. We can learn a new task by reusing some of the knowledge that the model previously had. And that's why we don't need to update all the parameters.
Okay, fine.
Raman,
Yeah.
I have a question. So you told that you will be fine-tuning just the attention and normalization layers, but you are
Yeah.
defining mask over blocks, and each block seems to contain a MLP layer as well. So
Right, right.
how does the freezing happen?
Sure. Yeah. So this, I just gave it as an example. I mean, this is not the exact thing. I just gave it as an example,
Okay,
but
yeah.
you can also treat it in the following way. So each element of the mask might denote fine tuning just the attention layer or just the normalization layer. It just depends on my use case, what use case I'm using it for. But
Yes,
I just wanted to explain the concept of a mask, basically. Should I continue?
Yeah, I think you should.
All right. So again, very briefly, under this setup, we have a pre-trained model, which is a VIT, which is pre-trained on ImageNet 21K or some of the bigger data sets. And we also have a binary mask. And what we want to do is we want to fine tune this model on a downstream task. It's a downstream medical data set. And we want to measure the performance in terms of fairness, or we want to measure the performance of the worst subgroup. And now I'll explain you basically the pseudocode for tuning or freezing a model components given a mask. It's that if I have a mask, what do I basically do with it? So one example of that could be, and I've also given the pseudocode on the right side. So one example of that could be if each element of the mask denotes a block. So in this case, you see this particular mask would say freeze the first block, fine tune the second block, freeze the last block, etc. Here I'm operating at the block level, but I can do the same thing for normalization layers. So if you see in this case now, I'm doing train module block.norm1, train module block.norm2. Basically, if my mask element is 1, I will train the normalization layers, or if the mask element is 0, I will freeze the normalization layers. And I can do mix and match of things. So now you see if the mask element is 1, I can train the attention and normalization layers together. And if the mask element is 0, I will freeze those things. So basically what I'm trying to show is that a mask can control, using a mask, I can control what part of the model do I need to train or freeze. That's the entire concept. But the main question is, how do I even search for this mask? Because you see, if the mask has 12 elements, there are two to the power 12 possibilities of different masks. And obviously we cannot train or use all of them. So how do we search for this mask? There can be different ways to search for this mask. One can be a random search, where each element of the mask is just generated randomly. So once I have a randomly generated mask, I will freeze or fine tune the model according to the mask, and I'll get the performance on the downstream dataset. But that's a very brute force way to do it. And again, a random search would not be efficient at all. Then there can be another way. It could be a gradient based meta learning approach where each element of the binary mask is a learnable parameter. So each element of the mask is learned. It's a parameter like torch.nn parameter, and it is learned during training. That could be another way to learn the mask. And
Raman,
the third, yeah.
so mask is a discrete entity, right? So how does gradient-based meta-learning work here?
So there are several ways to do it. Although we didn't go into gradient-based meta learning in this work, but what we can do is that when you'll if you do gradient based things, obviously you'll get some different values for each element of the mask, but then you have to threshold it in some way, and convert it to zeros and ones. So for example, I can say that if my mask element is greater than 0.5, I will make it 1, and if it is less than 0.5, I'll make it 0. I mean, you can do some kind of a thresholding.
Right, but typically in these kind of approaches, they just take one or, I mean, a few gradient steps. Within that few steps, will we hit the threshold? I'm not sure.
Yeah, so we
Yeah, I
didn't
also
really
have a
explore this
similar
direction that much.
question. Like when
Yeah.
you do thresholding, then how the gradients will be preserved? I was also thinking about the same lines.
So that's what I'm saying. We didn't really go into this approach in this work. I mean, I'm just discussing different schemes of how it can be done, but we didn't explore gradient-based meta learning.
Okay.
So the gradient-based meta learning is one way, and everybody is welcome to try it. If you have ideas, then please let me know. Then there is another way. What we can do is a gradient-free meta learning approach, where each element of the binary mask is treated as a hyperparameter to be optimized, and it's suggested by an HPO algorithm. So you guys must have worked with HPO algorithms when you're trying to find a good learning rate or a good weight decay or something like that for your task. But in our case, each element of the mask is a hyperparameter that we want to learn. So that was our strategy for this case. And this is a bit more explanation of the gradient free meta learning approach. So each element of the binary mask is treated as a hyperparameter, and it is proposed by an HPO algorithm. Over time, the HPO algorithm learns to propose better choices for the mask. And what our expectation is that the HPO algorithm will learn what kind of a mask, or it will learn to suggest particular values for a mask such that the fairness is improved. And I'll show how it works. But this is just this approach is basically, it's smarter and more efficient than a random search, because if you're doing a random search, the searching space is too big. You're searching in it randomly. You will arrive at a good solution or maybe not. But a gradient free meta learning approach is a smarter way to do that. And when you're doing this kind of an HPO, you basically need three things. You need you need to tell your HPO algorithm, what do I need to optimize? What parameters do I need to optimize? In our case, that is the binary mask. Then you need to give an optimization objective. You need to tell your HPO algorithm, what do you need to improve? So in our case, it is the performance of the worst performing subgroup in the validation set. We want to improve the worst performing subgroup. So that is our objective. And finally, you need to give a direction, an optimization direction. So our direction is maximizing. Basically, we want to maximize the performance of the worst performing subgroup in our validation set. So given all of this background information, now I'll introduce you the framework or the paper and the framework that we proposed in the paper, which is called FairTune. So it is basically a framework that can optimize the choice of parameters to be fine-tuned in a model to improve fairness on the downstream task. And I would like to explain the framework using this figure. So we start at the top where I've written HPO sampling. Basically, you have a randomly generated binary mask, and initially it would be random. You give this mask to your model, or basically, according to this mask, you freeze or fine tune different parts of the model, and then you fine tune your model on your downstream data set for 30 epochs, for example. And then you measure the performance on the validation set at the end of 30 epochs. So, for example, we had two subgroups, male and female. I measure the performance on the two subgroups, and I report the performance of the worst performing subgroup back to the HPO algorithm. So once this HPO algorithm had information that, I suggested this mask, and this was the performance of the worst performing subgroup, maybe I need to change certain values and maybe it will perform better. So now the HPO algorithm will propose another mask, and we will do the exact same thing. We will again train the model for 30 epochs. We will again measure the performance on the worst performing subgroup, and we will hand it back to the HPO. And then again, it will propose another mask. So basically, we will keep on proposing masks several times, and finally we would arrive at a mask that leads to a very good performance, and where the difference between the best and worst performing subgroups is minimized. Are there any questions on this thing? No? All right. So this is the framework basically. Again, it's the same explanation. Step 1 is HPO algorithm proposes values for different elements of the mask. Step 2, we apply this mask to our model, or basically we determine which parameters we will freeze and which parameters we will tune according to this mask. Step 3 is we fine tune our model on our downstream data set, and we get the performance on the validation set. And step 4 is the HPO algorithm proposes, again, we measure the performance on the validation set, and then the HPO algorithm proposes another mask given the result, based on the result. And this is very similar to when you tune learning rate. For example, if you're tuning learning rate using a same HPO algorithm, the algorithm suggests a learning rate, a weight decay, etc. You use those things to train your model, and then you probably measure the performance on the validation set, and then you send that performance back to the HPO algorithm, and then it suggests another value for the learning rate. And it's the same thing basically, but here we are learning the mask instead of the learning rate. So now I would like to address the question that was previously asked. So the mask that I was showing you until this time was a 12-bit mask, or it contained 12 elements. And what those 12 elements basically mean is that each element of the mask can denote basically either the attention layer or the normalization layer or something else at a time. I mean, I cannot say that the same element denotes both attention layers and normalization layers. The 12-bit mask denotes one of the things, but I can get a bigger mask, a 36-bit mask, and I can choose to, and now it gives me more flexibility, and it basically So I'll show it to you in the next slide, of how this works, of what a 36-bit mask means. So this is a 12-bit mask that I've been showing in the presentation. Each mask can either denote a block, or it can denote an attention layer, or it can denote a normalization layer. But it cannot denote all the three things at the same time. But this is a 36-bit mask. Here, 3 bits represent a block. So if you see the first 3 bits, 0, 1, and 0, they all belong to block 1. The first bit, which is 0, it denotes all the normalization layers in a particular block. The second bit denotes the MLP block, and the multi-head self-attention block. And the third bit denotes the MLP block. So now I have more flexibility. I can now, if I give this mask to my HPO algorithm, it can learn something like, freeze the normalization layers of block 1, fine tune the attention layer of block 1, and freeze the MLP layer of block 1. So now I have more flexibility, and I don't have to choose from just fine tuning the normalization layers or just fine tuning the attention layers. And our FairTune framework that I have proposed in this paper, it uses these things. It uses a 36-bit mask, and we have done ablation studies on using both 12-bit and 36-bit. But the final results that we have reported are on the 36-bit mask. And when we report the performance back to the subgroup, I report the performance of the worst performing subgroup, as I have been telling earlier. And this is a fairness specific objective. I can also report the overall performance without any notion of subgroups. I can just report the overall performance, and that is a general purpose objective. That does not tell us anything about fairness. That does not tell us anything about how the two subgroups are performing. But a more fairness specific objective could be reporting the performance of the worst performing subgroup, and that's what we have used in our framework. And then we compared our results to a bunch of different baselines. um, the simplest baseline is basically training from scratch, from random initialization. Then the second baseline is full fine tuning. Given a pre-trained model, I fine tune all the parameters of that model. Then there is linear probing, that given a pre-trained model, I will freeze the entire model and I will just fine tune the classification head. Then we have a bunch of established PEFT methods, such as attention tuning, which says fine tune all the attention layers, layer norm tuning, which says fine tune all the name layer norm layers, etc., and so on. And then we had certain methods that have been used to that has been proposed for fairness in recent times. There's a method called fair prune, which is a pruning method that removes certain layers, or it removes certain weights from the model, which it thinks promote bias. And there's another method that was proposed in CVPR last year. It is fair supervised contrastive learning. So all these things were our baselines, and we wanted to compare our proposal with these things. And then we also had a bunch of different data sets for evaluation. So if you see these data sets, the size of these data sets range from 420 to 220,000. Then we have a mix of different attributes, sensitive attributes, such as age, gender. Some data sets also contain information on race. Some data sets contain information on skin type as well. So we have different types of attributes, or protective, sensitive attributes. The data sets belong to different modalities. You had images of the eye, which is fundus images. You had CT scans of the heart. You had skin dermatology images. You had MRIs of the brain, and you had chest X-rays as well. So it was a mix of everything. So basically, this kind of analysis would allow us to evaluate our proposed algorithm in all different conditions. And this is one of the tables of result. You can check the paper for more results. But basically, if you, from a brief look at this table, if you see the rightmost column, you see that our method basically outperforms all the other methods with a significant margin. And We report three different things in our table. We report the overall AUC, which is just the overall performance across the whole data set. We report the AUC of the worst performing subgroup, which is min AUC. And we report the gap between the worst and the best performing subgroup. And quite simply, like our algorithm outperformed all the other methods and all the other baselines, basically. And we can also analyze the HPO. So once you run an HPO, and if you have used libraries like Optuna to do some kind of hyperparameter tuning, you might know that we can get these kind of plots at the end of our HPO. So the HPO can give you values on importance. So for example, here from this example, the HPO is showing that the ninth element of our binary mask was found to be the most important, which would mean that for a particular data set and for a particular sensitive attribute, fine tuning the ninth layer or the ninth attention layer uh, is probably the most significant thing to do. And then on the right side, on the right hand side plot, you see you see that we have ran the HPO for several number of times. um, Basically what this means is that we have trained our model with different masks for certain number of times, and after about like 25 to 28 number of trials, we see that the performance saturates. And what this means is that around the 28th or 29th time, the HPO was able to find a mask that gave the best performance. And after that, it was not able to propose any other mask that could improve the performance. So in about 25 to 28 trials, we found the best mask. And then once we did our analysis, once we ran all the experiments, we had several, and we analyzed the masks. So once you run all the experiments, you have a mask for each data set and each sensitive attribute in that data set. So we analyzed those masks, we plotted them using t-SNE, and we wanted to see a pattern. But instead, what we found is that there is no simple preference for any particular layer or component. So I cannot say that it's good to fine tune the first 5 layers of a vision transformer and the last 5 layers, and you'll get a good performance. There is no pattern, which basically means that each data set and each sensitive attribute uh, benefits from a different type of fine tuning. And it was the same thing. There was a high variability and probability of selection. So it might be possible that fine tuning layer 5 for one particular data set is the best thing to do, but it is also the worst thing to do for some other data set. So this was our algorithm, and we have some future directions what we can do. One of the directions is using some advanced HPO algorithms like Pasha. These have been developed by people in my research group. And then there is another algorithm which somebody pointed out earlier, is that we can use a gradient based meta learning approach, because currently our mask was 36-bit. So, and if you look at it, if you compare it with the number of parameters in the model, it is still very small. So if you want to search for every parameter in the model, you could use a gradient based method, and that could possibly lead to better solutions, and that we have left that for future work. Thank you.
Thank you so much, Raman, for that really awesome talk. So now the floor is open for questions if anybody wants to ask something.
Yeah, one more question. So regarding your data sets, I would like to ask like the number of features. Like, can you just share like what are the number
Yeah.
of features in each data set, or maybe one or two data set?
Yes, I'll just share the presentation again. Number of features. So basically, when we looked at previous studies which have done similar kind of things, what we saw is that everybody categorizes or creates just two categories. So for example, in gender, we will always have two categories of male and female. But in age, we can have many categories: age between 0 to 10, 10 to 20, 20 to 30, etc. But we need to binarize those categories. So what we did, for age groups, 0 to 60 was one category, and 60 and above was the next category. Similarly, for race, if our dataset had multiple races, we just made them into two categories. And yeah, so we binarize, and this is something that previous studies have also done, so we just followed it.
Okay, so I was thinking, like, suppose if we take this fundus first popular,
Yeah.
so it is some kind of image there. So it should be having some. I was thinking maybe in that point of view, like some pixels or some, hierarchical features out of those pixels. Not like that. You just use this gender, as you mentioned, like binarize two features for gender and for age two features below 60 and above 60.
Yeah. So
Okay.
sorry, what were you saying? Like, for fundus
Actually,
images?
I'm still not clear about that. Like, if I try to visualize the data which you have as a kind of table, so you say like 420. Suppose first data set 420. That means 420 rows are there, and the number of features I'm interested in, like how many features were there, number of columns I mean in that table. If it,
But it's an image. So
okay, so like okay, suppose if I say MNIST image example 64. So we have those 64 features.
right.
So, but these attributes, as you were mentioning here, age and gender, so those were like, suppose 64 pixel is that image, so 64 plus 2, one
No, no,
for
no.
age and one
So
for gender.
no, no. So I think you're confusing two different things. So age and gender is basically additional information that we have on this data set. We have the images. In this data set, we have 420 images.
Okay,
Um, I would basically use each. I mean, if you have experience with image classification, we just use an image, and we give that image to a feature extractor or a CNN
hmm,
or a vision transformer, any kind of model, and then the model gives us some outputs. The model gives us outputs on the performance. So
okay,
what I did is that instead of measuring the performance on the whole data set, I measured the performance for each different subgroup. I measured the performance for male people separately and for female patients separately, and then I
okay,
compared
sort of
them
like,
to.
yeah, sort of like clusterize the data, like for all the images for males and all the images for females, and then calculated the overall performance over male and female, like in
Yeah,
something like that. Okay.
yeah, yeah, yeah.
Okay, so one more question was regarding the HPO. I'm not aware about it. So can you just please explain a bit more about the HPO?
Sure. Um, so basically, if I give you the simplest example of an HPO, when we are doing, you might have heard of something called hyperparameter tuning.
Hmm. Yeah, grid
And
search,
basically,
basically.
yeah, a grid search or any different kind of search. But grid search can be very expensive when we are talking about deep neural networks, because there can be many different combinations to try in the grid. So what you can do, you can use something called Bayesian based methods, and I can probably share this as well. Um, I'm just opening it in another tab, and so basically, if you can see my screen again, um, this is a library called Optuna, and there are many other libraries as well. The easiest use case of these libraries is that it can help you in optimizing your learning rate, weight decay, etc. And that process is the HPO. But in our case, we wanted to learn the mask instead of learning the learning rate or
Mhm.
those different kind of things.
So these kind of, like suppose this kind of Optuna or the library, they just take in the parameter which you want to test on, and it will give okay for this set of configuration. This was the performance achieved. So internally
Yes.
they have some other algorithm to how to come to the best configuration.
Yeah, so Optuna has many different algorithms in order to perform that hyperparameter fine tuning. And I mean, you can take a look at the library.
Okay,
Um,
okay.
but if I did the same thing, I mean, I could have searched for the mask. I could have searched for this mask using grid search also, but then it would have been extremely expensive uh,
Yeah.
to search for this, because imagine you have to find if you have to search for 36 different parameters.
Hmm.
And there are two different values possible for each parameter. So in a grid search, that would have been 2 to the power 36 number of examples.
Yep.
So that would have been impossible to search. And that's why we need a smarter way to search. And the algorithm, the HPO that people usually use, and the one that I used as well, it uses a Bayesian algorithm in the background. You can read more about it. I've written about it in my paper as well in the appendix section. So basically, these all these HPO hyperparameter optimization frameworks, they have some kind of a Bayesian algorithm in the background that doesn't need to perform a grid search, but it can perform a slightly smarter search.
Okay, thank you.
Hi, I have a question. In the experiments, did you observe any pattern? Like, for example, if a certain configuration of the bit mask gave you a good validation AUC gap, can you pin down on what are the likely nearby values of W that are likely to give, close
Yeah,
to the observed AUC?
yeah, we tried to do that, and this was one of the observations at the end. We tried to do that. We tried to analyze all the masks that we had, but we could not find a pattern, unfortunately. Which basically means that if you have a new data set, and if you have a if another data set comes, I would need to use my
Uh,
framework again on this
so,
data set to
conditioned on a given data set, can you find patterns?
uh, so no.
I'm
For the
trying to ask this
same,
question to kind of understand if I were to
yeah.
define a kernel on the bit masks. Let's say I'm using a Gaussian process to kind of learn the mapping between W and the AUC gap. So this
Yeah.
GP will work only if I'm able to define a kernel between Ws.
Mm, I think I didn't understand that properly. Can you repeat
Yeah.
that?
So for example, let's say I take the first data set here, Papilla. On
Yeah.
this, if a certain W works, if
Yeah.
I perturb
Certain
the W,
certain
let's
what
say
works?
let's say you found a certain W star that gives you the desired AUC gap.
Okay.
If I perturb, let's say 1 bit in it randomly,
Mm-hmm.
will the AUC gap differ by a large margin?
Hmm.
How sensitive is the learned W hat from your algorithm?
Mm, I think this is something did not explicitly uh, we did not explicitly explore this, but if I remember from my experiments, um, so if I perform an experiment, for example, if I ran my experiment on the same data set twice, if I do just
Yes.
the same experiment twice, I will get two masks that are very, very similar to each other, but not exactly similar.
Ah, okay. Yeah. Right.
Yeah. So this can also mean that I mean there might be certain values in the mask that are not too important,
Mhm.
but most of the mask in the two experiments would remain the same.
Ah, okay. Yes. And also, if you can go to the slide where you showed the table, the results table.
Yeah.
So your algorithm kind of exploits the sensitive attribute annotations, at least in the validation dataset.
Yeah.
Which of the other Bayesian approaches leverage such annotations?
So FairPrune, the second last one, sorry, the third last one, and FSCL, the second last
Okay.
one, both of them, because they are also methods that were proposed explicitly for improving fairness. So we
Yes.
also have to give them this information. I
Information.
mean, they
Okay.
use this information in some way. Yeah.
Are they also bi-level kind of approaches, or do they tune on the training data itself?
FSCL is a single approach. I mean,
Mhm.
it's not bi-level. FairPrune, in FairPrune, you train the data, you train your model basically on your data, and then using a validation set, it is also not bi-level,
Mhm.
but it is two steps. But my solution is bi-level.
Bi-level. Okay. Got it.
Yeah.
Yeah.
Hi, Raman. Am I audible?
Yes.
Oh, hi. So my name is Atif. It was a great talk. Just I got added to the talk in middle, so I'm a little bit out of context. So I just wanted to ask, in your results section, you have shown that the accuracy from training from scratch was about 73. I think that's like the worst performing column, I guess. Why is that the case exactly? Because I thought, like, in fairness, biasness, accurate training from scratch is probably like the best, gives the best results, but at a very high computational cost.
Hmm. Yeah, that's a good observation. Um, I think because I was using the same number of epochs to evaluate all of them, that is why we get the worst performance from train from scratch. But I also feel that I don't think it is possible for train for scratch to give the best performance also. I mean, we could have improved on that performance if I would have trained it for 20 more epochs, for example. But it wouldn't have given a better performance than the other methods.
I see that's quite a bold claim, but okay, I'll take it. Thank you.
Oh,
Are
one
there
last
any other
question.
questions? Yeah, go ahead.
Yeah, so as you said, like you were focusing only on the performance over the worst performing subgroup, kind of. So did you observe any such an incident when, like, suppose we take an example of gender, male and female. So in validation, suppose there was a gap. The male group's performance was suppose some around 70%, and
Mhm.
female group performance maybe around 50%.
Mhm.
So your method will say, okay, that is having 50% accuracy, so we will fine tune it. So you were able to go from 50 to 60%
Mhm.
for the worst performing. But it may also would have happened like the performance which it was having on male from 70, it would have deteriorated. So any such
Yes.
incident did you noticed?
Yeah, so this is actually a very common scenario for methods that are proposed for fairness. And that is where people ask the question, what compromise are we willing to make? How much can we compromise the performance of the best performing subgroup to improve the worst performing subgroup? But in our case, we were essentially improving the generalization of our model by fine tuning it in this way. And because we were improving generalization, what I saw is that we not only improved the performance of the worst subgroup, but we also improved the performance of the best subgroup. We improved both of the performances at the same time. So, but it is also highly possible. What you said is very true, and it is very much possible, but we didn't see in our case.
Okay, great. Thanks.
Okay, if we have no other questions, I would like to thank the speaker again for his time. Raman, thanks a lot for joining us today.
Thank you so much for giving me this opportunity. And yeah, if anyone has any ideas and wants to collaborate, I'm open for that. Yeah, thank you very much once again.
Yeah, sure. So I'll drop a note in the Slack channel, and people can contact you personally if they want to, or ask questions in the questions channel as well.
Sure.
Thanks a lot, everybody, for joining. I am going to stop the recording and close the meeting in a couple of minutes.
Thank you.